Part 5 broadens the discussion from self-driving cars to physical AI. The goal is scalable embodied intelligence that can operate safely in complex spaces shared with people. Large language models succeeded because of one thing: the internet. Trillions of tokens of human-generated text. Training on that corpus gave LLMs world knowledge, common sense, and generalizable reasoning. Robots do not have an internet. Robotic behavior data must be collected physically, each robot in each environment performing each task, observed by sensors and annotated either by humans or by auxiliary systems. You cannot crawl the web for robot navigation trajectories. The data problem for physical AI is categorically different from the data problem for language AI. The path from current robotics to general-purpose physical AI is blocked by two distinct barriers. Barrier 1, no web-scale robot behavior data. Behavior cloning requires large quantities of demonstration data in the target environment. Barrier 2, no human modeling in context.
Robots operating in shared human spaces must predict and respond to human behavior to be safe.
A robot that cannot model pedestrian intent cannot safely navigate a crosswalk. The testbed for this work is not highways or freeways. It is the environment where most urban movement actually happens. In the United States, approximately 60% of all trips are shorter than 5 miles. UCLA partners with COCO Robotics, deploying autonomous delivery robots in real campus and urban environments as the real-world validation testbed for the methods in this part. To train robots for these environments, we need simulation. The world is compositional, or there is a God. This observation points at something fundamental about how environments work. The world is not a fixed list of named places. It is built from components. If a robot can understand the components and their relationships, it can generalize to any combination it has never seen before. Meta-Urban, published as an ICLR 2025 Spotlight, is a compositional simulation platform for urban environments. Instead of designing specific scenes,
Meta-Urban uses description scripts to procedurally generate environments.
The number of city blocks, intersection types, lane widths, sidewalk configurations, varying these parameters across different distributions, generates an effectively infinite variety of unique training environments.
The most important empirical finding from Meta-Urban is about scene diversity, not quantity. When you vary the number of unique training environment layouts and measure performance on unseen test environments, the relationship follows a power law. Diversity in the environment distribution matters more than raw volume of experience in any specific environment.
Scene diversity creates another problem. If training an agent to navigate diverse environments requires 180 GPU days on a state-of-the-art platform, the computational cost of experimentation becomes a fundamental barrier. This is the bottleneck that UrbanSim was built to eliminate. Moves the entire hot training loop onto the GPU, physics simulation, observation computation, and neural network inference all running on device with no CPU-GPU transfers in the critical path. After 3 hours of wall clock training with 256 environments, the agent reaches 41% task success rate. A single environment baseline reaches only 6% in the same wall clock time. 180 GPU days to 3 hours. The simulation bottleneck is resolved. Now, for the human modeling problem. Existing human motion datasets record human movement in isolation. Motion generated from these datasets walks through walls, ignores obstacles, and produces spatially incoherent trajectories. CityWalker is the first dataset designed to capture pedestrian behavior in the context of real urban environments. PedGen is a diffusion model for pedestrian motion generation conditioned on 3 input streams: scene context, body context, goal. The result, without context conditioning, generated pedestrians walk through obstacles and follow incoherent paths. With context, they navigate naturally, avoid barriers, and move toward their goals in ways that a robot interacting with them can reasonably predict. Simulation environments without realistic pedestrian models are often described as zombie cities. These agents don't react to robots, don't avoid each other naturally, and don't produce the social dynamics that real urban environments contain. PedGen begins the transition from zombie city to living city. When pedestrians are generated with scene-aware, goal-conditioned motion, the simulation environment starts to exhibit the emergent social dynamics. Vid to sim to video footage of real environments directly into interactive simulation. The pipeline combines two reconstruction techniques: 3D Gaussian splatting, mesh reconstruction. The combination gives a simulation environment where observations are photorealistic from 3DGS and physics are accurate from mesh. A robot trained in a vid2 sim environment sees and feels something very close to the real environment. This is what the full stack produces: a simulated city with realistic geometry, photorealistic rendering, physically correct surfaces, and populated by pedestrians that navigate, react, and move in ways that reflect real human behavior. A robot trained in this environment inherits all of that: spatial awareness, reactive navigation, and the ability to anticipate the kind of behavior it will encounter when deployed in the real world. The 5 parts of this tutorial form a causal chain of problems and solutions. Part 1 identified the fundamental limitation of single-agent autonomous driving. Part 2 identified the physical limitation of any single agent, regardless of its intelligence. Part 3 grounded the cooperative system in reality. Part 4 made the system efficient. Part 5 extended the entire paradigm beyond cars.
That's all 5 parts of Beyond Self-Driving. Thanks for watching.